Alright, let us start the next question. X of n is a discrete time periodic square wave with period n and amplitude 1. Non-zero samples extend from minus n1 to plus n1. Find the Fourier coefficients. So this is a discrete time signal, and what we have to evaluate is discrete time Fourier series because it is a periodic signal. Okay. It is a square, it's not a square wave, it's a square pulse. Okay, it's a square pulse, I have to correct it. This is a square pulse. Okay, with the period n and amplitude 1. If at all it was a square wave, it should be amplitude 1 and minus 1. So okay, so this is a square pulse. Non-zero samples extend from minus n1 to plus n1. So let's try to plot this signal for an accurate result. Okay, so this is x of n. As per the data given in the question, this is a discrete time periodic square pulse, right? Period is n. So since it is n, this sample will be n, or I can say this sample will be minus n1 plus n, right? You add plus n to get this sample, repeated sample, right? Or if you add n with this sample, you will get this sample. Okay, so this is actually n minus n1, right? And this is actually sample is actually n plus n1. Okay, so this is our signal. We have to find out the discrete time Fourier series, and we all know the discrete time Fourier series is given by I'm writing DTFS. DTFS is given by x of k, which is equal to 1 by time period of the signal, and sigma over 1 sigma over 1 time period. But here the non-zero samples are only extending from minus n1 to plus n1 within 1 time period. I repeat, within 1 time period. Okay, this is one complete time period. This sample to this sample is 1 complete time period. So within that time period, the only non-zero samples are from minus n1 to plus n1. So I am summating this signal from n equal to minus n1 to n equal to plus n1. Okay, x of n into e raised to minus j 2 pi kn by n. X of n is 1, right? For all these samples, x of n is 1. So 1 into e raised to minus j 2 pi kn by capital N, which is the time period. And since it is given the time period as n, you may be appreciably write the angular frequency also, which is given by 2 pi by n. Okay, let be there, right? So we have the DTFS. Okay, now what we have to do is we have to expand the summation. We have the summation here, we have to expand it. So while expanding, we have done many problems like this. While expanding, there is some samples which have negative values, right? Negative minus n1 to minus n1, and some values with 0 to plus n1, positive values. So we can split either you can split this summation and first summate the negative n values and then separately summate the positive n values. We have done many problems like that. I think there is yet another method for doing this summation, which involves both negative and positive values. Let me illustrate or let me use this problem to illustrate that method. Okay, I repeat, separating the negative and the positive summation, positive samples and summation is perfectly correct. You will get the correct answer. But since we have done many problems on that, I think I will change this method for this problem. Okay, so let us do this. What my aim is to change the negative and positive to positive alone, right? Here it is a mixed summation, negative and positive are there, but I need to do only positive summations. So I am changing, or I am doing a substitution. What can I do? What is the best method? Here I need 0. To get 0, I must add n1, right? And similarly, I have to add n1 here also, right? So what happens to this summation is, or before that I have to put some other variable m equal to n plus n1, right? I have added n1 to n here, right? n1 added with n here. So I'm calling this new variable as m equal to n plus n1. Okay, m equal to n plus n1, right? So what happens to this summation is x of k equal to 1 by n sigma over what is the value of m when n equal to minus n1? It will be 0, right? N equal to minus n1 means you put minus n1 here, you are getting m equal to 0. Okay, up to, and what is this upper limit? It becomes 2n1. n1 plus n1 is 2n1. So 2n1 e raised to minus j2 pi k by n into take care that no more n can be used because we are changing the variable to another one, m. So what is actually n from this equation? N equal to m minus n1, right? M minus n1. So we have to change or write m minus n1 instead of n. Okay, so this is very clear. That is 1 by n sigma over m equal to 0 to 2n1 e raised to minus j2 pi k by n into, I can split this summation into m into e raised to minus j2 pi k by n into minus n1. Okay, and you have to note that this entire term does not depend on m, so we can take this outside the summation, which will give me 1 by x of k is equal to 1 by n e raised to plus j2 pi k by n into n1, right, into sigma m equal to 0 to 2n1 e raised to minus j2 pi km by capital N. Okay, now the only method before us left is to expand the summation, which will give you 1 by n e raised to j2 pi kn 1 by n into, if you put m equal to 0, you will end up in 1, plus if you put m equal to 1, this results in e raised to minus j2 pi k by n, okay, into 1 maybe, plus next is m equal to 2, you will get e raised to minus j2 pi k by n into 2, okay, plus etc. And what is the last term? You put n equal to, m equal to 2n1. So e raised to minus j2 pi k by n into 2n1. Okay. Okay, now this is equal to 1 by n e raised to j2 pi kn1 by n into, what is inside the center bracket? This is definitely a geometric progression. And that is finite. This is a finite, not infinite. This is a finite GP, finite geometric progression. Okay, and you know what is the sum of a finite GP? What is the sum of a finite GP? That is Sn is equal to, if there are n terms, then a into 1 minus r to the power n by 1 minus r. This is the expression to find out the sum of a finite GP with n terms. So here what is a? First term is 1. Okay, what is the common ratio r? It is e raised to minus j2 pi k by n. Okay, and what is n? Number of terms. You can see number of terms is, here it is 1, second term, third term, fourth term, etc. up to 2n1 terms, right? And there is a 1 here. So totally 1, 2, etc. 2n1 terms plus 1. So there are actually 2n1 plus 1 terms. Okay, you take care not to make a mistake here. So there are 2n1 plus 1 terms. Okay, so the first term is 1. We are summating this. First term is 1 into 1 minus common ratio is e raised to minus j2 pi k by n to the power number of terms. Number of terms is 2n1 plus 1. So to the power 2n1 plus 1 whole divided by 1 minus r. R is still e raised to minus j 2 pi k by n. Okay. So this is the final answer. I can write it as 1 by n e raised to j 2 pi k n1 by n into 1 minus e raised to m in e raised to m to the power n is e raised to mn. So e raised to minus j 2 pi k by n into 2n1 plus 1, right? Yeah, 2n1 plus 1 whole divided by 1 minus e raised to minus j 2 pi k by n. So this is the Fourier series coefficients. If you want, you can still simplify this by taking, we have done a problem like that just the previous video. So we can take e raised to the half of this exponent outside, here also half of this exponent outside, so that the entire term becomes sinusoidal, right? Here it becomes a sinusoidal, here also a sinusoidal. If you want, I can write the final answer as 1 by n sine, it will become 2 pi k into what comes in the bracket, it will be n1 plus half by n. In the argument it will be n1 plus half by n whole divided by denominator will be symbol sine pi k by n for k not equal to 0. If you want to evaluate it for k equal to 0, you have to use the L-Hospital's rule, because giving k equal to 0 in the numerator and denominator will give you 0 by 0 form. So use L-Hospital's rule. So for k not equal to 0, this is the final answer, or you can end it here also. Okay, so that's the end of this question. All right, let's head on to the next question. Find the inverse Z transform of x of z using power series expansion technique. Actually, students, power series expansion is not in the syllabus under KTU. So you can either do it in any way of your convenience. But since this question, two other methods other than the conventional methods will be used. The conventional method, it is by using partial fraction expansion, but this question is a bit difficult to do in that way. So I think there are two other methods. The first method is using polynomial division. So whenever you feel that it is difficult to make this in a partial fraction form and to find the inverse Z transform, then you go for polynomial division, whether it is feasible using polynomial division. So to do polynomial division, we write like this, as though we do it for real numbers. So z divided by 2z square minus 3z plus 1. You might be remembering one thing I have already advised you. If at all possible, you just try to write 2 as this thing and z as this thing. Otherwise, you are going to confuse everything. At the end of your solution, 2 becomes like this, z becomes like this, and you will be in a confusion whether I have written 2 or z. Okay, so just take care of this. So z by 2z square minus 3z plus 1. So how to do polynomial division? First we have to find out a quotient that turns out when z is divided by 2z square. So what will be that? It should be there should not be a 2 here, so half into z raised to minus 1, right? You can confirm it by multiplying this term with the quotient. Okay, that will give the answer, right? 2 into half is 1 and z square into I think you're following. 2 into half is 1, z square into z inverse is z, that is z is perfectly right. So the quotient is right. So we can multiply this 2z square into half z inverse is z. Okay, but the multiplication doesn't end here. If you have to multiply this two terms, you have to multiply these two terms and these two terms. Okay, so what happens when you multiply minus 3z and half z inverse? It will turn out to be minus 3 by 2 into, sorry, minus 3 by 2 into z inverse is 1. Okay, so minus 3 by 2. And you have to multiply 1 with half z inverse. That will give you half z inverse. Half z inverse. Right. Now what we have to do is subtract these two. Subtract this polynomial from this polynomial. So z minus z will give you 0. And 0 minus 3 by 2 becomes plus 3 by 2. And 0 minus half z inverse becomes minus half z inverse. Okay. Now what we have to do is we have to find a quotient that divides 3 by 2 with 2z inverse. Okay, 3 by 2 with 2z inverse. What will be that? I think it will be you have to go for 3 by 4 into z inverse 2. You check whether it's right. 2z inverse into 3 by 4 z inverse 2. 2 into 3 by 4 will give you 3 by 2, correct? Z square into z inverse 2 will give you 0 raised to 0. That means 3 by 2 alone. Okay, so that is perfectly correct. But since this divisor and quotients are having more terms, I have to say that these two terms also should be multiplied with the quotient. So when you multiply minus 3z with 3 by 4 z inverse, what will happen? It will give you minus 9 by 4 z inverse, right? Minus 9 by 4 z inverse. So I have to write it. Oh yeah, right. Once again. So before that, our quotient is 3 by 4 z inverse 2. So first I have to multiply this thing with this thing. Okay, this term with this term, then this term and this term, and after that finally this term with this term. Okay, so when you multiply 2z inverse with 3 by 4 z inverse 2, you'll get 3 by 2. Okay, that is 3 by 2. Okay, minus, when you multiply this term with this term, it will be going to give you minus 9 by 4 z inverse. Okay, minus 9 by 4 z inverse. And finally, when you multiply 1 with 3 by 4 z inverse 2, you are ending with 3 by 4 z inverse 2. Now again subtract this term from this term. Okay, so what you will get is 3 by 2 minus 3 by 2 is 0. Minus 1 by 2 plus 9 by 4 will give you 7 by 4 z inverse. So plus 7 by 4 z inverse. Then 0 minus 3 by 4 z inverse 2 is minus 3 by 4 z inverse 2. Okay, so the remainder is still having a power of 2. Okay, we will find out one more question. So now the next question is, what quotient will result when 7 by 4 z inverse is being divided by this term, 2z inverse 2z square minus 3z plus 1? What will be the quotient? It should be plus 7 by 8 z inverse 3, right? It should be 7 by 3 z inverse 3. You have to check it whether 2z square into 7 by 8 z inverse 3 will give you exact 7 by 4 z inverse. It will give, right? So it will be 7 by 4 z square into z inverse 3 is z inverse. Okay. So again, some other terms also will become. I think we will stop the calculation here because this is recurring. This some other terms goes to infinity. Again, terms will come after the other, and it goes to infinity. So I think I can stop here the division. Fine. So what the quotient we get is this thing. Okay, we can truncate the quotients up to this term. Only 3 terms. Okay. So what I'm getting is, the question was x of z is equal to x of z equal to z by 2z square minus 3z plus 1 ended up in half z inverse plus 3 by 4 z inverse 2 plus 7 by 8 z inverse 3. I can write it as 0 into z raised to 0 plus half z raised to minus 1 plus 3 by 4 z inverse 2 plus 7 by 8 z inverse 3. And what is the inverse transform? What is the inverse transform? You're going to get, therefore x of n is equal to, inverse transform of 0 is also always 0. Okay, so the sequence will give you 0. Now what is the inverse transform of half z inverse? Half z inverse means it's an impulse shifted to 1 unit, right? So this is 1 by 2 and it is at n equal to 1, right? This is at n equal to 0. So 1 unit shifted means this is at n equal to 1. So 1 by 2. Okay. Now the next term is 3 by 4 shifted by 2 units, exactly right, n equal to 2. It comes at n equal to 2. Next is 7 by 8. Okay, actually it extends more than this, but we have truncated it. So this is the answer, the inverse transform. Now I have already told you there is one more method to do this. Actually there are many methods, but one more easy method to do this. What that method is, our x of z is actually it's given in the question as z by 2z square minus 3z plus 1. Now this is a question which is which you can find the denominator is actually factorizable. If you work it out properly, the denominator can be factorized as it is 2z minus 2z minus 1 into, you'll get z minus 1, right? 2z square minus 3z plus 1, right? So actually we can factorize this like this. Okay, what I'm saying is you need not do polynomial division, but if you find that it is difficult to factorize it, then you can adopt this method. But actually I'm saying this is actually factorizable. Okay, so many students may feel that it is not factorizable. For those students, you can easily go to polynomial division method. So others, if you feel that this is factorizable, you do it in factorizable form. So this is a by 2z minus 1 plus b by z minus 1. So a is equal to, what you will get as a is a equal to, you put z equal to 1 by 2 in this term. So 1 by 2 1 by 2 by 1 by 2 minus 1 is you will end up in minus 2, right? So a equal to minus 2. And what is b? I'm a little bit speeding up because we have done many questions like this, right? So in order to save time, I'm speeding up a bit. And what is b? B equal to, put z equal to 1 in this term. So 1 by 2 minus 1 is 1. So b equal to 1. Therefore, one second. This is a problem here. Yeah, if you do like this, right, you got what we are doing is wrong, but you need to know why it is wrong. Okay, so z by 2z minus 1 into z minus 1 is equal to minus 2 by 2z minus 1 plus 1 by z minus 1. So we got the partial fraction method, partial fraction of this transform function. And now what is the inverse transform? Do you have any standard inverse function that can give you a signal from this thing? No is the answer. Again, this thing, no is the answer. If at all, you listen, if at all this term was z by z minus 1, you would have written that the inverse transform is u of n. No problem, you're safe. Or if at all this term was 1 by 1 minus z inverse, then also u of n is again the inverse transform. But neither of the form is given. It is 1 by z minus 1. So you cannot do this, right? So that's what I have told you. This is wrong. So we have to slightly change something from the beginning itself. Okay, I'll tell you. Okay, I will tell you what to do. Before starting the partial fraction expansion, you write x of z by z is equal to 1 by 2z square minus 3z plus 1. Okay, now this x of z by z is equal to 1 by, you can factorize this denominator as 2z minus 1 into z minus 1, correct? Yeah, it's correct. So this is equal to, we have already done it as minus 2 by 2z minus 1, right, plus 1 by z minus 1. Okay, so this is the factorized form of x of z by z, not x of z but x of z by z. Okay, now listen. Okay, since x of z by z is equal to this term, I can write x of z is equal to, you cross multiply this z to numerator of both the terms, you will get minus 2 into z by 2z minus 1 plus z by z minus 1. Or I can write it as, I'm taking 2 outside. Okay, so these two cancel. So minus z by z minus half plus z by z minus 1. This is x of z. Now both the terms are perfectly in a standard form where you can simply easily evaluate the inverse Z transform. So what is the inverse transform? Therefore x of n is equal to minus is here. What is the inverse transform of z by z minus half? It is half raised to n u of n, plus what is the inverse transform of this term z by z minus 1? It is simply u of n. Okay, so this is the inverse transform, and it makes perfect sense. You might be thinking that this inverse transform is different from this one. It's not actually different, because you put n equal to 0, n equal to 1, etc. and calculate the amplitude. What happens at n equal to 0? At n equal to 0, this is minus half raised to 0 into u of 0 plus u of 0. Everything is, so this term will give you 1, minus 1, plus this term will give you 1 at n equal to 0, right? U of 0 is 1, right? U of 0 is 1. And this here it is half raised to, minus half raised to n means minus half raised to 0. Anything raised to 0 is 1, so minus 1. So what, minus 1 plus 1 will give you 0. Correct? The first term at n equal to 0, at n equal to 0, it is giving you 0. Is correct. Now apply this for n equal to 1. At n equal to 1, this term will give you minus half, u of n is 1. Okay, minus half into 1, plus for n equal to 1 it is 1. So this is 1 minus half equal to half. So at n equal to 1 the amplitude is going to be half. Correct? For n equal to 1 it is half only. And similarly in all other terms you are getting exactly the same signal. So these two methods will give you the same answer. Okay, that's the end of this question. Next question is, determine the discrete time Fourier series representation for the sequence x of n equal to cos pi by 4n and plot the magnitude and the phase response. So the first thought that should occur to you when you see this question is method of inspection. Okay, I've already told you, we have seen many questions whether for when you're given a discrete time or continuous time periodic signal and you have to find Fourier series, then you have to go for method of inspection if at all the signal is a cosine or sinusoidal or complex exponential. In these three cases, cosine, sinusoidal or a complex exponential, you have to adopt the method of inspection. Otherwise it is going to be very tedious. You will not get the answer. Okay, so we'll do this in the method of inspection. Before that, let me start with finding the angular frequency of the signal. You know, omega 0 by inspection, omega 0 is pi by 4. And why I'm evaluating omega 0 is to get the time period of the signal n equal to 2 pi by omega 0, which is 2 pi by 4, which is equal to 8. So 8 samples is the time period of the signal x of n equal to cos pi by 4 n. Okay, you will need this. Okay, so keep it here, 8 samples n. Now let us write x of n in a more easier form to get or to make the method of inspection convenient. That is, x of n equal to, you know how to write cos theta. Cos theta is half e raised to j theta plus half e raised to minus j theta. So this is half e raised to j pi by 4 n plus half e raised to minus j pi by 4 n, and I'm writing it as half e raised to j into 1 into omega 0 into n. Is that wrong? Not wrong, because omega 0 is nothing but pi by 4. So instead of this pi by 4, I'm writing omega 0. It's good, right? Plus half into e raised to j into minus 1 into omega 0 n. Okay, here it is minus j pi by 4. So I've written j into minus 1 into omega 0 into n. So that is our x of n. Let this be question number 1. Okay, now any periodic signal x of n can be written using discrete time Fourier series. It's a synthesis equation as sigma over k equal to 0 to n minus 1, where n is the period, x of k, the DTFS coefficient x of k, into e raised to j k omega 0 n. Okay, this is my DTFS equation, equation number 2, which is nothing but DTFS synthesis equation. Okay, now let us start the inspection. What we say by inspection is you inspect RHS of both these signals, because you're getting x of n from the LHS, right? The same x of n, so its RHS should be equal, right? So in the RHS or the first term, what is the signal part? Signal part is this, because it is got an n here. Okay, the variable is n here, so half is a constant, e raised to j omega 0 n is the signal. Now look at the equation number 2. Here you have the signal, and what is the constant that multiplies with the signal? It is nothing but the DTFS coefficient, and that is what we need to get, right? So x of k, which is the coefficient of the signal, is the DTFS coefficient for k equal to 1. X of k is a function of k, right? So e raised to jk omega 0 n, right? If you listen to the signal, it is of the format e raised to j into k into omega 0 n. So whatever comes between j and omega 0 n is going to be k. Here also e raised to j into omega 0 n, k equal to minus 1. So I can barely write, therefore x of 1 equal to k equal to 1. So x of 1 equal to half, right? This is e raised to jk omega 0 n. Okay, from this equation, whatever be the coefficient of e raised to jk omega 0 n, it will be x of k, but k is 1 here, so x of 1. So x of 1 equal to half. Okay, and what about this term here? K equal to minus 1. Okay, so what is x of minus 1? X of k becomes x of minus 1. What is x of minus 1? The coefficient of that term, that is half. So in this signal, for this signal, we have only two coefficients at k equal to 1 and at k equal to minus 1. So it is half in both cases. Therefore, we are asked to find or plot the magnitude and phase response. So we have to find the magnitude. Magnitude of x of 1 will be equal to 1 by 2, because it is a natural number. So just a real number. So its magnitude is going to be that number itself. And what is angle of x of 1? It is 0. For every real number, the phase angle will be 0. Similarly, what is modulus of x of minus 1? It is again half. It's a real number. And what is its angle? Angle at x of minus 1 is again 0 degree. Okay. Now we can very easily plot the magnitude response and phase response. So first I am drawing the magnitude response for k. Okay. And what we have is only at k equal to 1. This is k, so k equal to 1, and only at minus 1. Okay, at k equal to 1, what we are going to get is half. So 1 by 2. This is mod x of k. Okay, magnitude response. It is also called magnitude response. Okay, right. So at k equal to minus 1, we have again half, right? So half. So the plot is over, right? The plot is not over. Not over, because this is the specialty of DTFS. Why? Because DTFS in the frequency domain, what we are drawing is frequency domain. In the frequency domain, periodic. This is the important thing we have to notice. DTFS is periodic in frequency domain. So whatever we have obtained will be repeated. And what is the repetition? It repeats after every n samples. That's why we have initially found out n equal to 8. If you remember, we have calculated n equal to 8. So this same spectrum is going to be repeated after every 8 sample. So 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm not drawing according to scale. Okay, so this spectrum is going to repeat after every 8 sample. So what happens to where does this sample repeat? You add 8 to it. So 8 minus 1 is 7. So you're going to get that sample at 7. Okay, now where will this sample end? You add 8 to this, it will give it 9. Okay, and this repeats after every n samples. Here also you subtract n, so minus 1 minus 8 is minus 9. Here this sample goes to 1 minus 8 is minus 7. Okay, again it repeats. So this is the magnitude response. And what is the phase response? Phase response is no need to draw it, because angle of x of k is always 0. So here 0, again it repeats as 0. Okay, it's trivial to draw it. Okay, so this is the answer to this question. Okay, fine. The next question is, a discrete time LTI system is given by a difference equation is given. Determine the frequency response and impulse response of the system. You need to find out the frequency response and impulse response. So I will do it very quickly. What you have to find is, since it is frequency response, it should be Fourier transform. Okay, so you apply Fourier transform on both sides. Fourier transform on both sides of the difference equation. So y of omega minus half into e raised to minus j omega into y of omega is equal to, on the right side, x of omega plus e raised to minus j omega into x of omega. Why this e raised to minus j omega? It is due to the time shift property of Fourier transform. Okay, and now you can take out y of omega common from both terms. So you'll end up with 1 minus half e raised to minus j omega equal to, you can take up x of omega common from both the terms. So 1 plus e raised to minus j omega into x of omega. Therefore, the frequency response is given by the ratio of output transform to input transform. So output transform of y of omega divided by input transform is x of omega, which will give you 1 plus e raised to minus j omega whole by 1 minus half e raised to minus j omega. Okay, so this is the frequency response. This is the answer to one question. This is this is frequency response. Okay, now they have asked us to find out the impulse response also. So how will you find out the impulse response? Listen very carefully. This is a slightly different question. Okay, because why? Because what is the power of e raised to minus j omega in the numerator? It is 1. What is the power of e raised to minus j omega in the denominator? It is also 1. You might be remembering that for a transfer function, for a proper transfer function, the denominator power should be greater than the numerator power. Okay, but here the denominator power is equal to the numerator power. So what we do is you slightly change the approach. I am writing h of omega equal to 1 by 1 minus half e raised to minus j omega, okay, plus e raised to minus j omega by 1 minus half e raised to minus j omega. It is correct only, right? I've split this fraction into 2, right? So now fortunately the first term is in the form of a non-Z transform, and what about the second term? It is also in the form of a non standard transform. Why? Because I can write it as 1 by, first term is 1 by 1 minus half e raised to minus j omega. We don't have any confusion that. Plus second term is e raised to minus j omega into again 1 by 1 minus same half e raised to minus j omega. So if you know the inverse Z transform of this, inverse DTFT of this term, that same inverse DTFT will be applicable to this term also, but there is an e raised to minus j omega multiplication is there. What does that imply? It implies nothing but time shift property, right? It implies time shift property. This e raised to minus j omega correspond to time shift. Okay, you might be remembering x of n and x of omega DTFT pairs, then x of n minus n0 will be having a Z transform e raised to minus j omega n0 into x of omega. Okay, so here this e raised to minus j omega into 1, I can write it as e raised to minus j omega into 1. Okay, so the time shift is by 1 unit, so I can write it as, therefore the inverse DTFT will give you h of n, which is nothing but the impulse response. Impulse response is h of n only. So h of n equal to, what is the inverse DTFT of this term? It is half raised to n u of n, right? Plus, so the inverse DTFT of this term also is half raised to n u of n, but it is shifted by 1 unit to the right. So half raised to n minus 1 u of n minus 1. Okay, so this is the answer. But I would like to go one more step ahead, just for an information. It is not important in the exam point of view. If you write here, if you finish here, you will get the full marks. But for your information, I am going one more step ahead. What that method is here. What happens to the signal at n equal to 0? At n equal to 0, I can write h of n as, this signal becomes half raised to 0 u of 0. Half raised to 0 is 1. 1 into u of 0 is 1. U of 0 equal to u of n starts at n equal to 0, and it is having amplitude 1 at all amplitude, all samples. So u of n equal to 1, and half raised to 0 is again 1. So 1 into 1 is 1. So h of n equal to 1 at n equal to 0. Such signal can be also written as del of n, right? Del of n is also having amplitude 1 only at n equal to 0. So at n equal to h of n together, I can write it as del of n. Okay, so this signal is having a impulse here, right? And what about the contribution of this term at n equal to 0? N equal to 0, what happens at u of u of n minus 1 becomes what? 0, right? U of n minus 1 means it is a unit step function that starts at n equal to 1 only. So what is at n equal to 0? 0. So 0 is being multiplied with whatever this is. Okay, so you will get 0. So del of n plus 0, again it is del of n. So what I am trying to tell you is, for such improper transfer function, you will always encounter an impulse signal. That is definite. Okay, for whatever improper transfer function you are going to face, its inverse transform will always give you an impulse. So in this answer, if apparently you seem that there is no impulse, but actually there is an impulse. That is specific if you analyze it at n equal to 0. At n equal to 0, you are ending up with an impulse signal. And this is same for continuous time signals also. That also give you del of t if the transfer function is improper. Okay, so such systems are not practical. Yeah, you might be learning in control systems when you study the initial value theorem and all, right? Initial value theorem is not applicable for improper transfer functions. Why? Because the inverse transform will always give you del of t. Del of t is not practical. Okay, for any system, del of t is not practical. So in that case, these systems are non-realizable, non-practical. Okay, so this is the answer to this question.